Hello everyone, my name is Golsa Tahmasebzadeh from Leibniz Information Center for Science and Technology. It's a pleasure for me to present our paper, Few-Shot Event Classification in Images Using Knowledge Graphs for Prompting. Event classification in images is the key to multimedia analysis, especially for countering fake news. One of the challenges for the task is that the labels for fine-grained events are often sparse or ambiguous, and also existing images for such events are very limited. That's why zero-shot and few-shot learning is important. Recently, vision language models have shown promising results for various downstream tasks based on prompting. For recognizing challenging events as shown here, the static template, a photo of A, fails to predict the correct event. In this paper, we propose to use knowledge graphs to provide contextual information for events together with automatic prompt learning. Existing approaches for event type classification of images typically use convolutional neural networks to extract rich features from images which require a large amount of training data. Only a limited number of approaches rely on a small number of training samples. Existing datasets do not cover real-world event instances or have limited classes for fine-grained events. Prompting and image classification was primarily introduced by CLIP, contrastive language image pre-training. In the zero-shot classification, handcrafted templates are defined for classes. For example, this is a photo of a class name. The few-shot learning approaches, on the other hand, are based on automatic prompt learning techniques. Our goal in this paper is to propose a prompting approach to integrate knowledge graph information based on vision language models. This is the overall pipeline of the proposed few-shot event classification approach. I will go through different parts in detail. We have two types of hard prompts, class-specific and static prompts. Prompts based on class labels are the most basic hard prompts and consist of event label without much context. Prompts based on static templates are based on 80 different context prompts that were introduced by the CLIP authors Radford et al. Static hard prompts can be ambiguous. For example, skeleton, as mentioned earlier in the introduction. That's why we define class-specific prompts based on knowledge graph information which contains structured data for various events. The first one is based on Wikidata descriptions, which is short and concise but can still be ambiguous. For example, the description "a team sport played with bats and balls" applies both to cricket and baseball. That's why we introduce another prompt based on Wikipedia summaries, which provide a comprehensive and concise descriptions. Class-specific hard prompts contain contextual information to differentiate events, but can still lack details for fine-grained events, or sometimes could be missing. The soft prompt learning is aimed to learn tailored descriptions specifically for fine-grained events. For this purpose, we apply context optimization technique to learn soft prompts using few training samples. Based on CLIP's image and text encoders, we optimize these learnable tokens such that they are most tailored for each event label. During training, we freeze CLIP's encoders, and then we train M context vectors for each event label. For the inference based on the prompts that were introduced, we use a set of predefined events based on the dataset that we use. For each prompt, we extract the textual embeddings from CLIP's text encoder, and then the test image is fed to the image encoder. Finally, we get the similarities between these two, and then we sort the scores to predict the top key events for the given test image. We also introduce another prompt, which is called prompt ensemble, which is aimed at integrating synergies between different prompts. Wikidata or Wikipedia might not provide sufficient information for certain events, or could be missing, as mentioned before. When training data is available, soft prompts can create suitable descriptions for events. We propose to combine these prompts by averaging the similarities between these and the test image. In order to be able to evaluate the proposed approaches on fine-grained events, we propose a new dataset called Event Instances Dataset. We select different event types from Wikidata that have high societal and environmental impact. We query Wikidata for all the instances based on the instance of property. We collect the most popular instances based on the number of clicks on Wikipedia, and then we download the corresponding images from the associated Wikimedia Commons links. Here you can see the statistics of the dataset. We have 184 classes and 6,000 images. We randomly split the dataset to train and test. As you can see, the dataset contains various event types like protest, political campaign, election, natural disaster, and so on. We use two state-of-the-art approaches for comparison. One is event concepts approach, which learns concept classifiers for a combination of objects, scenes, and actions, and addresses few-shot event classification. The other approach is ontology-driven approach, which uses an ontology based on events mentioned in Wikidata. The architecture is based on ResNet 50. For supervised baseline, we use the popular linear probing approach, which is widely used in computer vision tasks. We extract visual features from images using CLIP's image encoder. We follow the same training method as CLIP paper. And for evaluation, we use top-on accuracy. Here you can see the benchmark datasets that we use for evaluation. The biggest datasets are visual event classification dataset with 148 classes and web image dataset for event recognition with 61 classes. Here you can see the results for zero-shot classification. As you can see, static templates outperform prompts based on class labels, which proves the fact that using more context is helpful in prompting approach. Also, you can see that Wikidata descriptions provide the best results for fine-grained datasets, such as RED and event instances. Finally, the ensemble of all hard prompts achieves promising results for all the datasets, as you can see in the bold. Here you can see the results for few-shot classification in two different settings, 5 and 30 number of images per class. As you can see, the ensemble of knowledge graph prompts and soft prompts considerably boost the performance for the majority of the datasets. Here we compare our approaches to linear probe. As you can see in the yellow part, zero-shot approaches considerably outperform linear probe given less than 5 training samples. And prompt ensemble provides the best results, as shown in yellow, which while needing considerably less number of samples, about 2, to outperform the zero-shot approaches and the supervised approaches. Can therefore recognize fine-grained events with few samples, which is very challenging as mentioned in the introduction. So this is a very important finding for many real-world applications and shows the potential of the proposed prompt ensemble and knowledge graph prompts. Finally, linear probe is superior when there is more than about 40 images per class. Here we can see the results compared to the state-of-the-art. As you can see, the ensemble of hard prompts achieves better comparative results to the state-of-the-art, which highlights the potential of zero-shot classification over supervised methods that require a large number of training data. Here you can see the results compared to the few-shot approaches. With few training samples, the ensemble approach is superior in most datasets. With sufficient training data, up to 30, it outperforms in all the approaches and in all the datasets. The qualitative analysis shows that if hard prompts lack context or are too short, soft prompt learning is more effective, which is the case in, for example, epidemic and protest events. But if there is enough context, such as geographical information and natural disaster events, then ensemble approach with soft prompts is more effective. Finally, to conclude, we proposed zero-shot and few-shot event classification of images based on vision language models. We introduced 4 different hard prompts based on Wikidata, Wikipedia, and soft prompt learning. We also proposed an ensemble approach which combines the synergies between hard prompts and soft prompts. We proposed a novel dataset of fine-grained events from various event types, and the experimental results have demonstrated that the ensemble of soft prompts with knowledge graphs reduces the need for a large training data, and the proposed approaches outperform the state-of-the-art on 6 different benchmark datasets. We make the code and data publicly available, and for future work we can experiment more advanced prompt learning techniques or integrate ontology information from knowledge graphs into prompts. These are the references, and thank you for your attention.